All right, so we've taken a look at using infinitely thin rectangles with integrals to find areas under curves. We've looked at using infinitely thin disk and integrals to find volumes of solids of rotation, solids of revolution. We're going to continue that concept by looking at volumes by using washers. And this can happen whenever your rotation has a missing circular piece in the middle. So let's take a look at what that looks like. Let's say that we're using this vertical axis of rotation and we want to rotate, let's say we want to rotate this region around that axis of rotation, right? So if I were to rotate this around, to kind of visualize it would be helpful to draw a mirror image across that axis of rotation. So something like this, maybe. All right, and then just like with disk, when you do washers, you slice perpendicular to the axis of rotation. Slice perpendicular to the axis of rotation. So here, let's see if green will show up better than orange. My axis of rotation is vertical, so I would pick some place here horizontally to slice. And so what happens is I get these 2 points to the left and these 2 points to the right. 2 points to the left, 2 points to the right. And so what happens is, if you imagine rotating this around the axis of rotation, all of this in the middle is going to be air. It's going to be hollow, and you're kind of going to have a weird bowl that has this concave down cavity in the middle. And so to approximate the area, we would use a washer, which is basically a disk with a hole in the middle. Okay, so you would start by going to your ends and drawing vertical lines like this. This will be the sides of your washer in this case. And then a washer, of course, is round, so you'd have this sort of round front. And so this would be the front edge of your washer, which would be like the front edge of a disk if we were doing disk. And then you'd have your backside wrapping around like this of your washer, right? So if it were a disk, it would look like that. But since it's a washer, you'll have this gap here. You'll have this hole in the middle. In fact, let's do it this way. Right? And so if you can imagine your washer here, looks something like this, where this is a hole in the middle of the washer. So this is your front edge. And then here you've got the solid kind of wrapping around this hole in the middle. And so you'd have a number of those stacked on top of one another, and you would add the volumes of each. Now, how do you calculate the volume of such a thing? Well, so if I were to draw it over here, it'll be easier to see. Okay, so there's a disk, and then you just remove the center. Okay, so that's a washer, and basically it's the volume of the outer disk. So you would take, let's call this the outer radius, R sub O for outer radius, from the middle to the outer edge, right? You take that volume of the whole disk without a hole, and then you would subtract off the volume of the disk that has been removed from the middle. So this right here is hollow, right? So you'd subtract off that volume of the disk. Well, so what you get is you get the volume of the outer disk, which is pi times the outer radius squared, times your thickness, t. So that's the volume of the whole thing if it didn't have a missing center, minus the volume of the disk that's been subtracted from the middle. So pi times your inner radius squared times the same thickness. So that's how you get the volume of a washer. Very simple. You just take the volume of the bigger disk minus the volume of the missing disk in the middle. And so this has some nice features. They both have a pi in common, so we'll factor out the pi. And they have a t in common. Your thickness is in common. Now, we could put it in the front with pi, like you typically do in an algebra class, but I want to continue the same format where it looks like pi times something squared times t. So I'm actually going to factor my t out to the right, which is kind of unusual. But you'll appreciate the beauty of this in a moment. When I factor out my pi and I factor out my t from both terms, all that's left is my outer radius squared minus my inner radius squared. And so this somewhat behaves like, it looks similar to the volume of a disk, where it's pi r squared t, but it's really pi times the difference of two r's squared times t. So this is kind of what we'll use to get the volume of a disk. Now, a common mistake that students make is they'll subtract the two radii and then they'll square the difference out here. Don't do that. You calculate each radius, you square them independently, and then you subtract, okay? So be really careful of that. So this is how you get the volume of a disk. Now, your disk can be oriented horizontally as such. Now, when you have a horizontally oriented disk, your thickness is measured vertically. So this is dy, okay? So in this case, your t, let's leave it here. So if you have a horizontal disk, you've got pi times your outer radius squared minus your inner radius squared times dy in this case. If you have a vertically oriented disk, so now the top and the bottom run horizontally, something like this, right? Then your thickness here, your thickness is a horizontal measurement, so it's dx. So the volume of this guy is pi times your outer radius squared minus your inner radius squared times dx. And so the big difference when you go to integrate these is, in this case, with a dx as your thickness, your radii will have to be expressed using x values, x expressions. And then over here for the horizontally, when your thickness is dy, your radii will be measured in terms of y. So from there, it's just integration as usual. We typically do not draw the disk with, or the washer with an actual measurable thickness. We usually assume infinitely thin. It makes it much easier to draw. I'll show you what that looks like real quick, because this is how I will do all my examples in an upcoming video. Let's go back to the one we saw before, where we were rotating this curve around this axis. Again, draw the mirror image, something like that. And I would pick a washer with a horizontal slice, and I would proceed as usual. So I'd make my slice and I'd mark all of my points across that slice, but I'm not going to give it any vertical thickness. It's going to be infinitely thin. So basically, it's just going to be a ring now. So the outer section of the ring looks like this, and the inner section looks like that. That's so much easier to draw. And so your outer radius goes from your axis of rotation to the line, and your inner radius goes from the axis of rotation to the curve, and your thickness is dy. Okay, so you would integrate that for your volume. You'd integrate it from, well, they'd have to be y values. So let's call that y value A, and then let's call this y value B. So you'd integrate from y, or from A to B. You'd have pi times your outer radius squared minus your inner radius squared, right? So you've got pi, put my square in the wrong spot. So you've got pi times the difference of your square radii times your thickness. And so that integral is going to give you the volume of the solid that you get when you rotate around this axis of rotation. Again, because this is dy, you would have to make sure to express both of your radii in terms of y, even though they are x measurements because they're horizontal. Okay, enough about the concept. I'm going to move on and make the video with the examples. I hope this helps. It can be difficult to draw. It's same as disk, you just put a hole in the middle.